I told something about the method of reduction of dimensionality, how it can be used to stimulate contact and frictional problems, and I promised that in 1 year I can tell more about it, and this is just what I would like to do now. There are two subtopics: onset of motion and advanced generalized frictional laws, and I do it in the reverse order. First the generalized friction law, then onset of motion. And first start with our general starting discussion point, what is friction? What is frictional coefficient? Of course, we all know that the more general, more well-known and widely used law of friction is Coulomb's law of friction. It states that there is no motion if the tangential force is smaller than the critical one, and then after that it is sum which is proportional to the normal law. The reality is, of course, more complicated, as we all know. There is some motion before the onset of the macroscopic slipping, and of course it is an important topic for many things. For example, for vibrations, if the vibration amplitude is smaller than this starting amplitude, then you cannot use the Coulomb's law of friction at all. And after the starting of the macroscopic motion, there is no real Coulomb's law. The friction coefficient does depend on all things, including the normal force, and that means that the friction coefficient does not exist. Of course, everybody tells about that other approaches, other frictional laws are needed, and they are indeed needed. The most question which I am asked from the industry, it is, what is the coefficient of friction, or what is the frictional law that they has to implement in some simulation of forming and something like this. And my approach, not answer to all questions, but what I suggest is that some problems can be understood, can be simulated using this method of dimensionality reduction. I start with a small recapitulation. I would like to remember you what are the play rules, so to say. If two bodies are in contact, then there are two rules. The material must be replaced by something else than in reality, and the form of the bodies must be replaced with something. And this has two independent things. Material replacement is independent of the form replacement is independent of the material. If you have, for example, an elastic continuum of space, then there is effective elastic modulus divided by I, 1 minus cosine square of the cosine ratio, and this half space has to be replaced by one-dimensional series of springs with stiffness, which is just this effective coefficient multiplied with the spacing. If you have viscoelastic Kelvin body with some viscosity, then it has to be replaced by a series of dash pods with 4 times viscosity delta x. If you have a more complicated arbitrarily linear rheology, then there is a simple rule, general rule, how it has to be replaced. The second thing is...
May I ask a question? Why do you have it in parallel? Why they cannot be in series?
They can be in series.
Yeah, there are two options, basically.
This can be general integral form. And if you have integral form in 3 dimensions, it is exactly translated into 1 dimension.
Okay.
Then the second independent thing is the form. If you have 1-dimensional form, no, 2-dimensional form, f as a function of r, then you produce 1 dimension. There are separate rules for bodies of revolution, rough surfaces, their combination, and so on, isotropic, non-isotropic. I start with bodies of revolution. If you have a body of revolution, then you produce one-dimensional form with this integral. There is transformation from three-dimensional to one-dimensional. And the statement is, and then there are a couple of other rules for adhesion and such things, and the rule is that if you put this one-dimensional bodies into contact, even with friction inside, and you do vertical or tangential movement, then the force displacement relations in this one-dimensional system will be absolutely exactly the same as a three-dimensional. It is very difficult to understand. In the meantime, we have real enemies who publish papers against this method because they cannot understand that the three-dimensional real system with special correlation can be substituted with one-dimensional with separate springs. But it is real proved mathematical theorems. The relation is really absolute. This is no approximation. It is exact method.
Can you explain what the GX exactly means? GX?
What
is it physical meaning?
It has no physical meaning, but I just show you examples.
Okay.
If you have parabolic body with curvature radius r in three dimensions, then you take parabolic body with half the radius. It is stretched by 2 times in the vertical. This is F and this is G. This is three-dimensional and one-dimensional profile. This is the only G is the one-dimensional profile, which the replacement dimensional profile. If you have cone, then you replace it with a cone, so to say, which is stretched by pi half. If you have some power function, then you replace it by the power function with the same power, but with this coefficient which depends on the power. And if you have something, then you take this integral transformation. For example, if you take the ball which is flattened, weighed out, then this is cut of this ball. Then this is equivalent profile which is calculated with the integral transformation. If you have cylinder with rounded borders, then you have every, and you can put it together, superimposed, and the statement is the three-dimensional contact mechanics and the one-dimensional contact mechanics of this displacement profiles will be exactly the same.
So you basically simulate kind of one asperity, yes? Or
if you consider bodies of revolution, then yes. But this is applicable also for fractal self-affine services, so I go further to this. Now, if you have adhesion, then there are also a couple of very simple rules. For example, if you put the body into contact and then pull, then the individual springs will detach if some critical value is achieved, and it depends on the size of the contact. And the statement is again, if you apply this rule, then the complete force displacement relation in 3 dimensions with adhesion will be exactly the same as in real 3-dimensional. For example, if you take the ball, then you will get the Johnson-Cannon-Rover theorem, completely exact. If you take cylinder, then you take exact cylindrical solution. If you take cone, you take exact 3-dimensional cone solution. And this is now for arbitrary position, but if you only need the adhesion force, and adhesion force is the point of instability. You pull, and then at some moment it gets unstable and detaches. And this instability, the condition for the instability is very complicated to formulate 3-dimensionally. You have to have this force displacement relation and look where it is it gets installed. But in one dimension, it is trivially simple. The difference, the ratio of this critical stretching of one spring divided by the size of the contact must just be the slope at the border of the contact. And this is the critical condition. You get the, and the coefficient does depend on whether you do experiment under controlled force or under controlled displacement. It is different. I can generalize this part that, as a matter of fact, this method of dimensionality reduction for bodies of revolution does nothing new. Everything is known, but it is a pocket edition of the complete contact mechanics. All solutions, all classical solutions which you do know, all classical solutions which you do not know, all solutions which are spread about century-long history of contact mechanics are compactly given with the simplest rules which each student of first semester can calculate in 3 lines. As a matter of fact, it is already some things which is valuable, which is easy to implement in numerical simulation systems and so on. So even if one says there is nothing new in this. But of course there is something new, and this is the rough contact. Not really new, but also very rough contacts are much more complicated to simulate than bodies of revolution, and this method can also be applied to this sort of surfaces. Of course, again, one has to replace the three-dimensional rough surface by one-dimensional substitute surface. The rule is formulated in the terms of the spectral density of the surface. If you have two-dimensional spectral density, the square of the Fourier components is a function of the wave vector, then you multiply it with 2q, and then you have one dimension. It is the approximate rule. In reality,
may I interrupt?
Yes.
Can you explain more about that C two-dimensional functional density and that Q? What it really means?
The Q is wave vector. It is 2 pi divided by the wave length.
Okay.
And this spectral density can be, as a matter of fact, defined as something which is proportional to the square root, to the square of the modulus of the Fourier transform.
Okay.
So it shows how it is the contribution of the given wavelengths in this spectrum. Of course, this spectral density defines the art of the what lengths are contributing to the surface, and this is what defines the two-dimensional surface, and this is what defines the one-dimensional line. And you can recalculate. In reality, there is a more complicated rule, which we also do not know, but I do not tell in details. But for typical first exponents, typical self-affine surfaces which we have with first exponent about 0.5 to 0.8, it is just 2k cubed. Just multiply with y vector and 2, and it is okay. Or in the same interval, it is really a simple rule. You take the two-dimensional surface, make a one-dimensional cut, and this cut has the spectral density 2q c to d, so it is already the substitute surface. This is not universal rule, but for the true interesting part of the surfaces which we have in practice. It is a simplified rule which is really simple. So you even not have to calculate the spectral density and to ask what is the spectral density. You just take the surface, cut it, and you get one-dimensional replacing surface. Now, of course, because we thought about this method as an engineering tool, it is giving in some sorts nothing new, it is for applications. So we made very much of verification. First of all, theoretical verification. Verification of correspondence of three-dimensional calculations to one-dimensional calculations in bodies of revolution, with self-affine, with combined profiles, and so on. This person does in his dissertation all proofs for bodies of revolution. He proved that the three-dimensional and one-dimensional as formulated are equivalent. And for rough surfaces it is not possible to give analytical solution. So here Roman Port did three-dimensional calculations with self-affine surfaces, very large range, and compared it with one-dimensional. This person, Kirchner, made the same with viscous. He invented self-affine three-dimensional surfaces in viscous and made three-dimensional calculations and compared them. And here I would like to show you a couple of results showing the quality and the errors of the method. First, what the results which you will see here, they speak about indentation of rough surface into elastic half space. If you have a rough surface, and we considered rough surfaces which is self-affine with some first exponent. Here are some kinds of self-affine surfaces with first exponent 0 up to first exponent 2. And this spectral density, one-dimensional, has then this form. It is power function of the wave vector. We consider this sort of densities even in this region and in this region, even in more white region. Completely, this is a complete white noise surface, so to say. And these are smooth Hertzian light. So all spectra which one can imagine of surfaces is included here. And we found that the stiffness is for all these surfaces is power function at small forces, is power function of force with some power alpha, and this is this alpha as a function of the first exponent. This is some region where they are really self-affine, and there is even the theoretical prediction, analytical prediction for this part. Then there is some part here, and then there is some part here. Here you have just smooth one asperity with this Hertzian contact, and the alpha is 1/3. This is a result for Hertzian contact. Here is something like Greenwood and Williamson. It is completely independent, large, high and independent asperities, and this is true fractal. Larger and then smaller and then smaller and so on. And now they coincide. These causes are true three-dimensional boundary element simulations. And red line is not approximation. This is one-dimensional. Because one-dimensional, one can do as much as you need. You can get really completely continuum line. It is, and we really understood theoretically why this and this are the border the first exponents, what is the physical meaning of this? We gave the theoretical approximation for this part, and the student is exact result for small forces. And here you see the stiffness as a function of force in some non-dimensional unities. For small forces, this is a theoretical prediction. The three-dimensional, one-dimensional must give the same result. This can be proven theoretically. For large forces, they are exact due to construction. They are always exact, three-dimensional, one-dimensional. The method is constructed in this way. And only a thing where it is not guaranteed that they are exact is the intermediate region. For first exponents, again, in this region that is typical, 0.5, 0.7, 0.8, you get also almost completely correct result. And for very small first exponents, there is error about 20%. So these are forces from 10 to minus 3 to complete contact, of course, further contact.
Yeah. I'm sorry, I'm not asking questions. Valentin, when you have these roughness measurements, that's a roughness, but when we are, let's say, in breaks, in addition to roughness, you have a waviness. Yes? Can you incorporate a waviness? So you have, let's say, Hurst 0, h equals 0. You have wave, which is on larger dimension, and you measure this h0 within that.
Yes, of course.
Can you incorporate?
Of course, because roughness here is understood as non-planarity in general sense. This is what was simulated here were surfaces without long wave cut off. So they have non-planarity on the larger scale and then non-planarity on smaller scale and so on.
Yes.
Of course, it is incomparable.
That's what our question is.
So on the larger scale, you still will have not complete contact, but some contact spots, and on the smaller scales further, and so on.
And then the question comes, maybe in this spot you have h0, in this spot you may have h1/2. Do you think it's general?
I think it is inside the statistics. Oh. But and of course the method is not applicable not only to self-affine. If you have more complicated spectrum, you can still use it. Mm-hmm. It is just as for forms, the simple forms, the simple rules for the bodies of revolution are for power function. But if you have any form, you can still recalculate. The same for rough surfaces. There are simple rules multiply with q if you have self-affine. It is more complicated integral transformation if you have just a rough surface, but it still works. You can combine body of revolution and rough surface. Here you see again these points is true three-dimensional boundary element calculation of a ball with roughness on it, and this line is what is coming from one-dimensional simulation. Of course, it is for us it is of course because we are completely sure that this works. But you see that it works also to combine profile.
Sorry, what is that L? What that means? If you could come back, that's stiffness divided by L times some effective modules. Yeah?
So that's the interesting thing that in all these calculations, the size of the system may play a role.
Yes.
And the h, the roughness, the small h, the large h, Hurst exponent and small h roughness. The small h may depend on the size of the system. But if you always have to look to the size and to define the h, the roughness, which is corresponding to this size.
Yeah. Actually, that's what I meant when I asked about baby.
It is, yes.
So that's the parameter.
Yes, this is really a finite size system theory. So now, because we were attacked very strongly, I and Marcus Hess wrote a book which will be here in September, which we submitted already, which contains all the proofs and applications, but is regrettably in German. We plan English translation, but
oh, don't worry, we can speak German.
We're going to actually get a free copy though. Regardless.
Oh yeah, it would be nice if you can send me a copy.
Yes, I can send you. Before, just now, in this submitted form, because it is completed.
Yeah.
Sure. So you have here some things which I did not. Tangential contact, rolling contact, adhesion with elastomers, which I did not spoke about. And of course there is appendices, exact solutions, and how it is proved, how it is made. Everything is contained here. Acoustic emission with involving contact, how one couple this to macroscopic dynamics, how one couple to microscopic friction, and so on. Everything is.
That number 19, you substitute some material properties by Radok's method?
But the viscoelastic is based on Radok.
Yes.
Yes.
Okay.
Because Radok's method is in principle is a statement that if you have elastic solution, then you get viscoelastic. And we have elastic, and we show how to get viscoelastic. Now, application to the friction. I will show only results for simplest elastomer, Kelvin, body, parallel, elastic, and viscous elements. And I take self-affine three-dimensional surface, recalculated in one-dimensional, recalculate the elastomer in one-dimensional set of springs, and consider two types of surfaces. Plane on the average, but of course plane means they have still the largest plane length, and or superimposed. I will show for cone and roughness.
Now, Valentin, you used to roll this ball, yes? That's what is happening.
This is not rolling.
No.
This will not rolling. This is
sliding the ball.
Sliding. So these are two simulations. This is just simulation of self-affine fractal against Kelvin body. What you have seen was self-affine surface with the ratio of largest to smallest space scale 10 to the power 4 for 25 velocities and 10 forces. This was calculation which no video is calculation. Which if you take because
may I ask that mu divided by grad?
By gradient. Gradient is just the average gradient of the complete surface. Gradient, slope.
So, yeah.
RMS slope. Not RMS slope, but square root of the RMS slope.
Yes. And those forces change. So you have the first one is blue, then green, and then.
So, first of all, as a function of velocity, as theory predicts, so to say, as everybody knows, it will increase its velocity and then come to plateau for Kelvin body. And you see something like this, but it also depends on the force. If you have this is small force, this is large force, the ratio is 10 to the power 3. And then, for example, If you have here on the plateau, then you have almost no dependence on the force. If you are here, then you have dependence on the force. If you take just another surface, because this was simulation for one realization, then you get something different. The realizations as in the nature.
Now, can you comment on that profile? It's increasing originally, then reaches kind of a peak, and it goes down. And when you go with smaller forces, normal forces, then that peak there disappears.
Yes, at larger forces.
Is it?
This is smaller forces, this is larger forces. At larger forces, it is average. So this means that here you had something like one peak, small peak, and you were on this peak, and if you put it, then you have average and this is.
I have a really bit hard time imagining what is the mu over gradient.
Yeah, I agree with it. It's not mu over gradient. What do you mean by gradient? Can you go through that
It's
again?
a slope of roughness, yes?
The gradient, this surface
The
is
slope of the ball.
these surfaces are characterized mainly by two parameters. The roughness, it is RMS Z,
Yes.
and the gradient is RMS slope.
If you draw it on there, does he a pen?
Whiteboard, yeah.
This is something like roughness, and this is something like gradient.
Yes. And you calculate it as an average or?
Yes, if I take average, this is H,
Yes.
and if I take practically, so this is what I call gradient.
Oh, okay.
And this is not only on the convex, but just characterizing the complete surface. On the complete surface, this is gradient of the average gradient of the surface.
Now, it seems to be a constant in your case, yes? When you,
It is.
It is constant, yes?
No, it depends on the smaller scale. This part depends mainly on the largest wave,
Mm-hmm.
and this part depends mainly on the smallest wave.
Vocalized, yes.
Yes. And of course, it depends on how smaller scales you take. So you can have completely similar surfaces, but they will have different frictional behavior because the smallest wavelength, which you do not see, is different, but it determines the frictional coefficient time.
You know what is also a little bit confusing to me? When I read all those papers, when they show friction versus speed, yes, which you basically have,
Yes.
but divided by gradient
Where's
versus
the
speed.
stiction on that?
If you
Stiction.
Stiction.
Yeah.
What is stiction?
What? Static friction. I talk about that. Static friction.
Static friction.
yes,
If you have this model which I explained now, then you have no static friction.
yes.
You have to introduce the static friction.
Oh,
But-
okay.
but of course
that was my question because normally when you may I just
Yes.
when you have these hooks, you have here friction somehow, and here is the speed, whatever, and you have something like this.
Yeah.
When here in this region it's controlled by maybe creep, and in this region is controlled by actually momentum or inertia. So, and in your case, you have this divided by this gradient, and your dependence is like this, yes?
But first of all, I would like to say that for rubber, this dependence, mu as a function of v, a beta of logarithm v.
Oh,
So we can see this region. It looks like this one. This is a typical. And this is about 1, and this is about 0.1. This is a true static friction of rubber, and this characteristic velocity is 100 of millimeter per second. So this is practically static friction. But if you move very slowly, then there is still no static friction. But there is static friction at very low, real true static friction of rubber is small. What we see is kinetic friction at small velocities. And this part is practically this one. And I consider this one, and this part is in true rubber, but if you have Kelvin mode, then you have this part, no. It will be simply with this also.
And Valentin, on that initial part of your dependence, I see there is some vibration to it. Is it just calculation or is it real? That you know what I mean?
No, it is.
It is real. Here, you have some noise there.
Ah, this name. I think this is just the definition of
just a plotting.
Plotting error.
So it's a smooth line.
Yeah, it's just discrete points really.
It is, yeah, more or less smooth line. It is not smooth, this larger oscillation. They are really simulations. This is.
So you are showing us this part here, yes?
Yes, this is practically this part, because in reality, even in this, if we, I will show later, even with Kelvin, it looks more like this. It is small decrease, but not very large, 30% or 20%. So, and this is, so to say, cone, rough cone. Of course, similar but different in detail, and if you look to the numbers, it will be different. The qualitative behavior is increasing, and that getting some plateau will be, of course, the same. If you take another realization, then you will give again another result, but approximately the same. And now, of course, because it is calculating very rapidly, then one can do parameter studies, and this, what I will speak about, is based on about 100,000 simulations for different values of shear modulus, viscosity, the smallest wavelengths, the Hurst, 11 Hurst exponent, and so on. And the typical form of the friction coefficient is a function of velocity in logarithmic logarithms of velocities. And this one, it is increasing, getting plateau, and then decreasing again. This is dependence for different forces. The same dependence as a function of velocity, but for small forces, you see that the forces are in interval of forces is logarithmic or exponential increasing. So this is, you see that this is some linear dependence, but on logarithms of force, and here is double logarithm. It is logarithms of mu and logarithms of velocity. And then again some power dependence, but with another alpha at small forces and larger forces. One can show from the general, both from the results of simulations, from the general dimension considerations, that the friction coefficient, if it is power function of force, then it has to have such general construction. So there are some parts, empirical results, for example, we see that mu is always proportional to the square of the gradient. And in this part. And it is only dependent of F divided by the shear modulus. If we change both, then we get always the same result, if other things. And then only this form can be, and then the only thing which we have to get is this power alpha. And these are results of alpha for different, it depends only on the Hurst exponent, and we really have also some theoretical explanations, theoretical derivation, and this alpha must be h divided by 1 plus h. You cannot read it, but it is h divided by 1 plus h, and it is, you see that it corresponds more or less to the empirical.
Hertz divided by 1 plus
by 1 plus hertz. Hertz divided by 1 plus hertz. So it should be 1/2 at hertz 1, and it should be 0 by hertz 0. So, and all the results can be brought into one law of friction. And the quality is seen here for six Hertz exponents. The calculation and the lines is this law. Independently of what parameter you take, you get the correct results. So this is the construction is not so complicated. The frictional coefficient normalized to the gradient is a function of only two parameters, of velocity and force, but again dimensionless combination for velocity and dimensionless combination of force, and even not from these parameters, but of the ratio of these two parameters, or ratio of function of v and function of n, fn. So I have wrote here. And what are the parameters? For example, if this dimensionless force is force divided by the shear modulus, roughness, and the size of the system. If you are on this plateau, then you have something which does not depend on anything. It is just gradient and nothing more. It does not depend on the force, it does not depend on the velocity, it does not depend on the size of the system, on the roughness, on nothing, only on the gradient. If you are in another part, it does depend on everything. It does depend on the size of the system, on the force, on the roughness, on the velocity, on everything, but not arbitrarily, but in this relatively simple form. For example, if you ask, we know that the frictional coefficient generally depends on the force. Is it dependent on the force or on the pressure or on what? My answer is not just on the force, not on the pressure, but on the force divided by the length of the system and the roughness. And this is an empirical prediction which is general. This is valid not only for every self-finite, as a matter of fact, for every other self.
From physics point of view, you have normal force expressed as a dimensionless normal force,
yes,
whatever, expressed as a real normal force divided by shear modulus. Why is it shear modulus? Can you tell a little bit more? Why is it normal? Is it not a normal modulus? If I have a normal load, do you assume?
Yeah, you know, I consider this as an incompressible, as a Lestonier, as an incompressible modulus. So it is just characterized either by elastic or by shear modulus.
Oh.
This elastic modulus with aesthetics is just 4 times the shear modulus.
Yeah.
They are connected. So you can take it another modulus, but then the coefficient will be different. It is just elastic modulus, one of them. It is only one which characterizes completely the system.
Now, again, I'm sorry asking so many questions. You do this for elastomers. What about, let's say, metals?
I have chapter 16 in the book.
Well,
when I also address this problem of plasticity and other things which are going in the direction of. But I must be scientific. I say just now it is elaborated and applicable surely for elastomers with arbitrarily linear rheological But about metals and other things, I will speak in the second part.
Oh, okay.
If I still have time. But the frictional law, I can only calculate in this thing for elastomeric, not for metals. Because for metals it is connected with plastic deformation, and I would not like now to say, oh, if I think about it and I work in this way.
Just as an aside, taking it on from there, is that we go in braking, is that you're not considering metals, you're not considering elastomers, you're considering friction pairs, that's one against the other. And in this case, it appears that you're just looking at a body. What's the other bit? Are you saying it's a sphere? Or are you saying it's a cone? And what is the material of the other bit? Do you understand?
This is in this case, the materials are the elastomer and the rigid body, the rigid rough body. It can be everything. It can be steel, aluminium, everything which is harder than the.
Considerably harder than rubber, the elastomer. So here's a ball sliding on.
I mean, in nowhere in there, you've got the gradient of this asperity, but you have nowhere in there the diameter of the sphere that's going to approach that gradient. And I would have thought that would have been important. That is the depth of the impression of the ball as it approaches that gradient, and indeed the angle of the cone as it approaches that gradient. There's no reference to that at all. I mean, if I took that gradient that you've got on there, and where you've drawn that line, if that is part of a cone, then it's hitting that the gradient of the cone is equivalent to the gradient of that asperity. Does that not make an effect? The actual geometry of the object that you're impression.
Yeah, maybe to avoid misunderstandings. This is a result for plane, not for cone. This is
for a flat surface.
For flat,
pure flat surface.
Yeah. So nominally flat, but in reality containing some long wave components, but not a cone. No.
But that again, it goes down to Peter's question: is why have you got G there and not E?
It is the same. It's
a function of the Poisson's ratio. There's a difference between the two.
Yes, but yes, of course. As a matter of fact, here the complete theory is formulated in the terms of E. But here I put E with this Stern, is equal for G.
For G, that's what it knows.
Assuming that it is incompressible. If it is not incompressible, then here stands something else. And I know what is it, but just not now. I have to sit down and write. And then I can exactly tell what is the true coefficient.
Valentin, why do we have this vibration there? Can you explain that?
What vibration?
Just vibration related to friction.
I do not know. but I would like to draw your attention to this thing. I'm sure that this is an important thing. It tells us that the force divided by the size of the system is important. That if you get something, then the generalized frictional law has to be developed in these terms, not in pressure or something like that. I look what this is another topic. This was the end of the generalized law.
So coming back to what Peter just said, the vibration, you have any thoughts about how this can lead to vibration? What is your thinking?
I think there are so many mechanisms so that I cannot give answer. Of course, sometimes the frictional load does play a role, sometimes it doesn't play a role. Further, this is a stationary. But if you move and then start to move with another velocity, then we simulate it. Then you have something like Dieterich's and other models is rotation, and this is a more generalized law because of course for true simulation or for dynamic simulation you have to take this into account. I think I cannot answer from this directly.
Next year.
No, maybe next year I can do this because, but it is not a joke, but true, because what we are working now on are the hybrid models. We just take a system with frictional contact and simulation system dynamics without inputting the frictional load, simulating the frictional load together with the system, because it takes no time to calculate the friction. This is
Now, you know what's interesting? Oh, sorry, did I
No, I'm just going to say it's that the vibration may come from the elastic recovery, because what you're getting there is that as the surface runs across the asperator, it can do two things. It can either shear it, you've got debris, you've got wear, or it can deform that elastically, and that means it recovers. If it recovers, then it will recover with some sort of, like anything would recover, it would vibrate.
So you stretch it, you release it, and
and those continuous things, if like these asperities, continuously vibrating, give it a very high frequency. And I think I said once is that all noise starts with a very high frequency, in excess of 50,000 hertz, and then we'll come down into something that's audible. And we never realise that, because we generally record at 20,000 hertz and never up to 50 or 100,000 hertz. And if we did, then we might see the system, all the system is vibrating at these very high frequencies. That cascade down to an audible frequency.
Yes, I think so. I probably, we'll talk
That
about
might be an answer to why you start a vibration off.
But I think that we have to have definition of what is vibration and what is not vibration, because friction is always a stationary process. Here you have, if you this is each point is averaged over time. This is just the experiment where you and if you resolve it in time, of course it's vibrating. But we do not call it vibration. It is just
friction. We've got an infinitely long body, and we haven't got that. We've got a discrete body, and so what we've got is a discrete body going over these asperities.
Yes.
And once it's passed over them,
yes,
there is some recovery.
Yes.
After it's passed over them, it's that recovery that we suggested it may be the source of vibration.
That's vibration.
Yeah, because it was
And vibration means noise cannot be without vibration.
Right. I mean, the noise is just a special case of vibration.
Oh, no, you're on there.
Oh, I don't know. You can have noise without vibration?
No, but that's what he's saying, is that noise is something you would hear,
Right.
isn't it?
Yeah.
But you can have the vibration there, but you can't hear it.
Oh yeah, no.
Yes,
Noise, the noise is kind of one limited
small
interval of vibrations.
Right.
Yeah.
But it's still vibration. It has to be vibration.
Yeah. It's just that we can experience vibration through noise, but we can have vibration without actually
and it's still vibrating at larger frequencies. Yeah,
that's what I'm saying. Really.
I probably will show
I mean, we're sat in this room now, these walls are probably vibrating away. Maybe very low frequencies, but they are. You know, there's no, the tables are, everything is.
Everything vibrates.
It's vibrating.
So essentially, I think what we are saying, what we are thinking is when there is a sliding of two bodies against each other, inherent characteristic is there is a vibration.
The adherence.
Inherently, there is vibration.
Yes.
That's what we measure.
Or how we measure, or that is the next question. But this sliding motion is always associated with the vibration. So whether it's a 40K or 20K, or you can hear it at 10K, there is vibration.
I agree.
The theoreticians, the nanotribologists who make it with atomic force microscope, they have found that if you have no elastic instabilities in the contact, then you have no friction at all. It is averaged out. So you have to have unstable macroscopic to have friction. Otherwise, there is nothing.
How will we validate that now? How will we validate it?
How we validate? So there are two types. The first type is done the theoretical validation, because it is one-dimensional and three-dimensional, and it is most done. We do three-dimensional calculations and compare it with one.
Yeah, but that's what I mean by validation.
But validation with experiment. With experiment, yes. This is what we do now. This is what I have to promise for the next part. And the last experiment, I will show you to this problem of validation. But maybe to the second part of it, the first part, the incremental, the preliminary split. If you load the static contact, then there is some movement without macroscopic sliding, and only after some time it starts to slide.
That's what is happening in fretting. Fretting.
Yes, it's fretting. Yeah.
Now, how long is this part?
How long?
Yeah.
It's very interesting. It is very. How long is the part?
I'm wondering if we should need a 5-minute break or something. Can we have 5-minute break?
Maybe we will do 5-minute break, and then yes.
How long are you going to take?
I think 10 minutes or something like this, or 15 minutes.
Yeah, let's go ahead. Let's go
No, I think it might be another 30 minutes. Well, it's a good stuff, you know.
So if you have just a parabolic contact and loaded and some friction, assume now friction in the contact, and you load it, then first, even if there is no sliding at all, if you glue it, then you still have some movement due to elasticity. And if you have some friction and not gluing, then at the border there starts sliding, and then this is dependence of the sliding, the displacement in the horizontal direction as a function of applied load, and you have first elastic behavior and then some sliding, and then this is for a parabolic contact, this is for a conical contact. It is very interesting. I did not know it earlier. I got it from the method of reduction of dimensionality, but it is exact three-dimensional result that the maximum tangential displacement before macroscopic sliding is this so-called Mindlin factor. It is the relation of the tangential and normal stiffness. It is for nu 1/3 is 1.3. It is just the indentation depth multiplied with the frictional coefficient. It does not depend on the form. You can have ball, you can have hole, you can have rough surface, you can have everything, cylinder. If you indent it to D, then at mu multiplied with D, you will get starting the moment. very, very simple. So, in principle, the dependence of this preliminary slip, preliminary displacement before starting slipping, depends on the normal force, for example, exactly as the indentation depth depends on the normal force. And this is a normal context which I've spoken about in the first part. Of course, I have this, you have it for every, and we have it for every rough types of rough surfaces and so on. And so you, for example, if you have hertz, then this is this dependence of the normal force. If you have cone, it is 1/2. If you have self-aligned with a Hurst exponent, then this is dependence. For very, very, very rough surfaces, where h is 0, you have logarithmic dependence on the force, and the tangential displacement has the same order of magnitude as just roughness multiplied with the frictional coefficient.
One short question. Mu is the same value for the stiction mode and for the sliding mode, is that right?
Yes.
Okay.
And now this is a one-dimensional one act where you move only in one direction. But what happens if you move a little bit, then move back, and then move again? Then you have a complicated stress situation. But it is difficult to describe theoretically, but it is easy to describe numerically, because there is in the chapter 18 of the book, it is proved that the tangential contact with constant friction coefficient in dimensional reduction model gives exactly the same result as 3-dimensional. You just implement one-dimensional system, and so here some maybe in the water is stick slip drive, which is moving. I think I had shown it last time. Which is moving due to such sort of moving of the ball. If you move it with small velocity, then it takes the slider, and if you move rapidly back, then it slides. And so you can move the slider in one direction. The stick slip drive. Yeah. I think I just show you results and comment them. If you have such slider, then you can generate some force. It's moving, then pressing on some spring, and then it is generating force.
Can you describe that slider a little bit more?
So this is the body, which is moving in this direction, or this is the same but moving in this direction.
And those black half spheres, or what is it?
These are Rubin spheres.
So and it's elastomer.
This is no. This is steel. This is steel, and this is sapphire.
Sapphire. Okay.
Is that just to give a frictionless surface?
Yes, frictional. These are frictional surfaces. There are 6 sapphire balls which are moving this. And sapphire balls are moving in this. This is half ball, and they have piezo's here and here, and they are contracting in different phase so that it is rotating. It is not really moving, but it is rotating inside. And you
have the lower part, the black or white one, and you have those wheels there.
You have, this is just applying normal force.
Okay.
You have to press it. This is such spring, and this is spring which is
shear force.
Yeah, to generate force. It is moving, and it is then stopping due to pressing on some. This is nothing more. This is just some. There is no ball. It is just a spring.
Now, why do you? So the normal load is applied from the bottom, and the top one is kind of rigid, but it's still on springs. Yes, the top. That sapphire half.
It is sapphire here and sapphire here, and this is pressed from both sides, of course. But just from construction, of course, from one side.
And this is moving in which direction?
This direction.
These are moving in this direction to the right, and then there is first here some space, so it is moving and then it's pressing. And you can measure the force which you have here, and this force is here, the generated force, and this is the amplitude of the oscillation. And of course, if you have amplitude smaller than this slipping, then you have nothing. You just move it back and forth, and you have to slip in one direction. So you have some amplitude after which it starts to generate the force. Before this, and you can see here how good is model this zero amplitude, this preliminary slip, which is connected with preliminary slip. Now I have to tell you, there is a topic which was described in literature in many publications. There are many elaborated frictional laws which are used to describe it with many parameters, and no gives good result as a function of normal load, for example. All depends. Now we have simulated this system with 6 sapphire balls as it is constructed, and these are experimental results, and dotted line is the theoretical calculations, including the rotation. And the calculation has no fitting parameters. It is elastic model of sapphire, of steel, the radius, the frictional coefficient measured, no fitting parameters. So this complete frictional law, including pre-sliding, which is used here, is just a pure contact mechanics, which has to be done. If you do not consider the contact mechanics, then you have to invent some frictional laws.
Now, Valentin, when you do that, you don't generate wear debris in between those balls and the
Wear
debris, yeah. When you finish your experiment and you look at that surface, is it still as it was before, or is it somehow changed?
I do not know exactly. The experiment is done not by me, but in Oldenburg, by the robotics department, who just do it and investigate. So, and then the last part is the validation. Now we are going to the validation and the development so that we can really describe the particular system. And for example, we do such simple experiment. This is a polymer band and a steel ball, and we just move it about 1/2 meter. And now I will show to show you, which you know, of course, the difference between theory and praxis, the result of 1,000 experiments, just 1,000 at the same, 1,000 times. So it is at the beginning. This is position along the band. You apply some velocity, this rising band, as a function of the coordinate. You have different friction coefficient, so to say, that is formally defined frictional
So there's one velocity, yes?
This is one velocity. You move with just constant velocity along this strip.
The same path, repeated.
There is only one.
It's
only one run. It is only one run. And now you will see as a video just 1,000 after another. How it is developing. And of course, we have to describe it also in some way, and to decide what we have to validate. This is how it's changing just with doing experiment further and further. The frictional coefficient gets smaller, and then it is another interesting feature. After some time, it starts to develop some way from here.
That's what we would call a conditioned surface of it.
Yeah, it's conditioned, but after that, you have stationary behavior when some wave is going from one side to the other, but wave in the sense that you make 10 experiments, and if it develops, then you take the second 10 experiments, it is developing from one side to the other.
What you're doing now, you're now putting history into the wear path.
Yes.
So you're running along the path,
Yes, of course.
running along the path.
Of course, it is in principle what Ostermeyer described on the larger scale. What is weird debris and everything. It's something like this is happening here.
In this case, you're burnishing it because you've got a steel ball,
Yes.
minimal wear. You've got a
Polyurethane.
you've got a polyurethane, which is not going to really wear. It's going to burnish. And depending upon the load, you're just going to burnish a path backwards and forwards.
Yes.
Until you've got a...
Only one side. Only one side.
Well, whatever. You know, whether it's going forward or backwards.
Yes. So
You know, if we go forward, lifting it
the
from the
initial
back.
state we call burnish.
What is the
Yes,
speed,
exactly.
Valentin, and what is the temperature there?
22 degrees, speed
83 millimeters.
10 centimeters, maybe.
Be sure
10
to
centimeters per
take
second, approximately.
And,
Yeah, no, and it doesn't heat up when you do that.
I think it heats up, but it is
Cool.
sometimes it is cold.
Valentin, in addition to all this, there should be one more parameter we call it
Humidity, yes, yes. Oh, yeah, humidity. I know, humidity. Humidity. Yes.
That's a good. I wanted to ask that question.
And the hour of the day, but at least humidity.
Will it be non-hygroscopic? Will that? It'll be non-hygroscopic. Nothing will be absorbed in the water in that case. The only humidity is going to be surface.
Right.
That's all.
But I think part of these experimental conditions, recording of the humidity
Humidity is of course essential. It's
It
essential.
goes with it.
It is in any case.
But-
There is capillary food, there is lubrication.
But Valentin, after you finish, that polyurethane is that surface when you make that track is different from the
It's
beginning.
different.
You can see
It's
by
different.
making
Yes,
it
that's
definitely
different.
even, and I believe your
It's
temperature is higher if you measure the temperature.
I think it was finally not so much higher because we have the thermocamera, and if it would be higher, I think he just waits. After some experiments, he waits.
That's another parameter. How much you wait before you go next time?
Ah,
You see, you can do it.
No,
Look at it.
it's going half a metre at 83.3 millimetres per second.
But then he erases it,
So-
goes back,
Yeah.
pushes it back, and goes.
Yeah.
Yeah, but if you have a look at that, if you look at the speed, it's 0.083 metres per second. So you've got 30 times 0.083. It's 2.4 watts that you put into it as a track.
But when you do it very quickly,
You're not though, you're doing it at 83.3 millimetres per second.
but there is a time between he finishes and he goes back and he
But it's going
starts.
over half a metre, and so what you've got there is that you've got something in the order of, if you divide 500 millimetres by 80, that's 4 seconds. 8 seconds is the whole cycle time, something in that order. So it's plenty of time to lose that heat that you're going to put into there. So it'll be sit there.
Now, if you look at that infrared camera still, what I see, when you do this, something like this on glass, much slower speeds. And when you look through that glass from the bottom, you go this slowly. Normal force, I have 10 newtons, and I have stars shining.
Yeah, I would bet that temperature is the room temperature, and not a measurement of the surface temperature.
Yeah, exactly. So what I think, you are conditioning the surface slowly due to
This is sure,
Yeah,
of course.
and then it stabilizes. It's
Of
like
course.
running.
It's the speed of your hand when you're doing
Yeah,
that.
yeah,
Very slow.
yeah.
But it is interesting that it is not stabilizing completely, but there is some
Some wave.
which is then
And I guess you are having some wear debris in there.
yes.
And you're going to get a band wave there, you know, from the material. Are you not going to get a band wave in front of the...
I think it is really, we have not measured the form with such precision, but it looks like such a wave which is really moving due to
Because
wear.
that would influence it. I mean, it's fundamentally you're grenelling something and then you're pushing it along, and it's got this. It must have a wave like water, a band wave in front of it, and that's going to give you an additional force, which is going to be seen as maybe a coefficient of friction. And maybe that is not the case, because if you change that now from a sphere to a block, you will get something entirely different. And the same material, that is steel, but it's a different shape. Put it on there as a flat, and you'll get a different coefficient of friction. I would gamble on that because of that bow wave effect.
With the block you have, in any case, very much problems because of sharp.
Yeah,
harmonics.
yeah.
They will come in fragments.
Yeah, well, whatever, yeah. That's a problem.
I think we have to finish the
So you have more slides?
to go to bed.
Oh, that's
I don't know.
very interesting.
Yeah, very good talk.
You're going a lot quicker without me to do it.
Mathematics for me is fun.
You see, I